So next week, we will learn all about Python. On Tuesday, we'll cover Python in general as a programming language. On Thursday, we'll cover the Python libraries relevant to machine learning. I know a lot of y'all already know Python, so Tuesday might be boring, but if you don't know Python, there'll be a lot of material. Okay, so last class we talked about generalizing evaluation metrics, or where we left off was generalizing evaluation metrics to multi-class problems where you're not predicting binary outcomes, but predicting between multiple outcomes. And we talked about macro averaging, and at the very end we rushed through micro averaging. So I just want to cover micro averaging again a little bit more slowly, because I skipped some steps in the sake of time last time. So here we see a confusion matrix, the same we saw last time, where we have the true value of y on the as the columns and the predicted value of y as the rows. And we want to use this confusion matrix to calculate the micro average. The last time we jumped straight to the pooled confusion matrix, and I kind of said quickly how we got there. Let me show you exactly how we get a pooled confusion matrix. So what we do is we create individual binary confusion matrices, so 2x2 confusion matrices for each class. And so, for example, for class 0, we'll compare the class we care about versus every other class. And we'll do the same thing. And the same thing for class 2. So what we could do then is fill in each of these confusion matrices. So for example, in this one, 0, when 0 is predicted to be 0 and it actually is 0, that's 8 in the big confusion matrix, that goes here. And then not 0 would be 1 and 2. So even though that's 10 and 1 on the top row of the big confusion matrix, that collapses down to 11 because we sum them up because it's everything that's not 0. We do the same thing for every and then the pooled confusion matrix is the sum of these three individual confusion matrices, which we showed the arithmetic for last time, but it might have been a little bit mysterious as to where that was coming from. And then again, the overall precision is then calculated as you would calculate precision for a binary problem. So in this case, the precision would be equal to 268 over 268 plus 99, which would be 0.73. We did that calculation last time. If you remember, we did macro averaging, and that got 0.6. This gets 0.73. We ended last class with a note that people tend to prefer macro averaging because when you sum up everything like this in micro averaging, it skews the results towards the overrepresented classes in the data set. Yeah.
So in the pool confusion matrix, it should be this should sum up to 3 times the normal confusion matrix. You summed up all the cells.
Mm-hmm.
That's still going to sum to 3 times the normal confusion matrix.
Yeah.
Okay.
Exactly. Okay. So let's go on to the next metric. Yes.
I have a question.
Sure.
So can you repeat how you got the class 2 row matrix? I don't understand how you got A3 and 33. So you have class 0, class 1, class 2.
Uh-huh. So for class 2.
Yeah, so how did you get the class 2 matrix? Like the 4 elements in that? Okay, so 200 is that, but how'd you get, I guess I don't see how you got 33 and 3 there.
So let's see. So let's start with 2 and 2. So for class 2, when y equals 2, and when y is predicted to be 2, that's 200. So that gives us that diagonal. And when y is not 2, and y hat is predicted to be not 2, that would be the sum of every, let's see, that would be the sum of basically this inner matrix. This is the matrix where y is not 2 and y hat is not 2, and that sums to 83.
Oh, okay.
And that's that logic extends to the rest of the matrix. Any other questions? Okay. Okay, so next evaluation metric.
To 83.
Yeah, 60 plus 10
Oh,
plus
yeah,
5
yeah.
plus 8. Okay, so F1 score is something that I actually was planning to cover earlier and I accidentally skipped through it. This is a common evaluation metric in machine learning. It's used all the time. Instead of reporting precision and recall, we can take what's called a harmonic mean of precision and recall, which gives us the following formula. So 2 times precision times recall divided by precision plus recall. And the reason people like to use this is that it penalizes extreme values. So for example, if you're trying to calculate the F1 score where precision is 0 and recall is 100, F1 score is going to be 0. If you have a situation where precision is 90 and recall is 10, it's not going to be the average, but it's going to be closer to 20% using harmonic mean. So it's really penalizing. If one of the metrics does not have a good performance, then the entire thing has not so great of a performance. So that's why we use the harmonic mean. Okay, so that's just a metric to know about because you'll see it in a bunch of machine learning papers doing classification.
So harmonic mean of anything is just 2 times the sum, two times the product over the sum.
Yeah.
Okay.
And there's some math to explain it, but I don't want to go into that today. There's a analogy you can look at in terms of what distance do you go when you drive a certain speed versus if you have a fixed distance, what's the speed it takes to get there? Yeah.
Very intuitive way for us to understand what F1 means.
No, so F1 is just think of it as a metric between precision and recall. Think of it as kind of like an average of precision and recall, but
It's not conceptually, but just what does F1 stand for? Does it mean anything?
I forget. Yeah, I don't know. Yeah, I think it does, but I don't know. Does anyone remember what F1 score means? Yeah, that's a good question, though. Let me write a note to look that up. I never looked into that. I just blindly used it in a bunch of papers, but maybe I should know. I know what it is, I just don't know why it's named that. Interesting question. Okay, so let's go to zoom out now and talk about the general evaluation process for machine learning. So in machine learning, you tend to have a data set, which I'm going to draw as a line. So this is our data set. And often what you do is split the data set into sections where you use a portion of the data to train the model, training set, and a portion of the data to test the model. You don't use to train the model, and that's the test set. Yeah.
We still under micro averaging, or this is only?
No, whole new section.
Oh.
Yeah. Let's draw a line and make it lower here. And okay, whole new section. So how we evaluate machine learning models. So yeah, we split up our data set into a train set and a test set. So the training set is what we use to learn the model parameters, learn theta. And the test set is what we use to test the learned parameters on unseen, in quotes, data. That is data that were not used to train the model. That's basically all there is to it, but let me write this out in pseudocode. And the pseudocode is going to look really similar to what we do in Python. So let's just really go through this. So in pseudocode, we might have our data set, and a lot of the work in machine learning is getting your data set into this format. So you might have your X data, which is what you want to use as the inputs to your model. You might have, let's say you're doing a classification with a 3-dimensional input space. So maybe one data point looks like this. Another data point looks like that. I'm just putting random numbers here, but another data point looks like that. I'm gonna do this 2 more times. Another data point looks like that. And a final data point looks like that. So just to be clear, one, 2.3, data point 4, data point 5. That's what we're going to use as the inputs to the model, and you also need to specify the desired outputs to the model. So you might put that in a variable called y data. And let's say this is binary classification. So we might get 0, 0, 0, 1, 1. And again, these correspond with each other. So this 0 would correspond to data point 1. This would correspond to data point 2. This would correspond to data point 3, data point 4, data point 5. And let's just be crystal clear. So that corresponds with that. That corresponds with that, etc. So the model given 3, 4, 2 as input should predict 0. The model given 1, 1, 1 as input should predict 1 according to our data set. So it's on you as Python programmers to get whatever data you have, whether it's images, or we talked in lecture 1 about how to represent different data types as numbers, convert it into numbers, and get it into this format where you're splitting up what you're using to predict with what you're trying to predict. X is the input to the model, Y is the output. You specify it as X and Y usually when you're writing code as well, or at least that's the convention. So let's now take that and split it into a train and test set. So the next step is to split data into train and test set. So for example, with this example, X train might be the first, or the training set might be the first 3 data points, and the test set might be the last 2 data points. So X train, just to be super clear, I'm going to write it out, be 3, 4, 2, 3, 2, 1, what was it, 4, 8, 3. With the corresponding labels for the training set being Y train, and that would be, let me, just for the sake of example, I'm going to switch up the labels to 0, 0, 1, 0, 1, so that we have examples of both classes in the training and test set. That's usually a good thing to have. Okay, so Y train will be 0, 0, 1. And we do the same thing for the test set. So X test equals 1, 1, 1, comma, 3, 8, negative 5. Those are the last two data points in our entire data set, held out not to train the model, but to test the model. And the corresponding test labels are 0 and 1. So this is pretty close to what you actually end up doing in Python. Of course, in real world, the data is not only three-dimensional, and these are technically NumPy arrays. We'll learn what those are next week. But you know, other than that, this is pretty close to what you actually do in coding. And now I'm going to show you the process for training the model in pseudocode, but it's going to turn out that the pseudocode is going to be basically exactly the same as what you can do with the modern machine learning libraries, which is pretty cool. That's to say that you can do machine learning without understanding what's being done. But we'll learn in this class what's being done, of course. So we train the model on the training data and test on test data. So let's say you were doing logistic regression. How would you use these data in code to train a logistic regression model? What are the steps? Well, first you would create a variable, and there's a library we'll learn about next week that literally implements all the methods we'll learn in the first half of this class for you, so you never have to implement them yourself. We'll cover deep learning soon, and for those you actually have to specify the model. But for the first half of the class, where it's very standard techniques, it's all implemented for you. So we make the model, and then to train the model, we say we take our model variable and we call dot fit, fitting the data. And that takes as input our X train and our corresponding Y train. So that now we have a trained model for
Is there a dot or an underscore between X and train?
it's an underscore.
Okay.
Yeah, you can't have dots in variable names in Python. So then, to get the predictions of the model, we might create a new variable named ypred, stands for prediction, which is the output of running model.predict with our test data. And then to evaluate the model, let's say we want to get F1 score, which we just learned about. You might say the F1 score, and there's literally a function. Actually, I don't know if it's exactly called F1 score, but a function that does this, that will take the true value and the predicted value and give you the F1 score. So in 4 lines of code, once you've gotten all your data set up, you can do machine learning, and we'll learn those libraries next week. And homework 2 uses these libraries, but homework 2 is about finding what's the best model with the best hyperparameters. But it's pretty light on coding. That's why they're so close in due dates with each other. But the reason I showed you this was not to teach you these libraries, because we'll learn that next week, but really to outline the overall steps of the machine learning process. So we get our model, we fit our model to the training data, we then make predictions on the test data, and we compare the predicted values with what the true values are and use those to calculate the evaluation metric. So these are the steps of the machine learning process. Any questions? Cool. Okay. So moving on. In the real world, we don't just split it into train and test, but we also have what's called a validation set. So we'll split it into train, validation, and test. And these three things are very different. Just to draw that out. Typically, the training set's much larger than the validation and the test set. So this portion might be the training data, validation data, and test data. What we do with the training data is the same as before, same with test data. So I'm just going to put quotes there, same as before. What we do with the validation set is tune our hyperparameters. We learned about some hyperparameters already. For example, even though we didn't cover it in too much depth, we talked about regularization strength, which is set by the ML engineer, and we gave it the value lambda. So like that, or another example is for logistic regression, the logistic regression decision threshold, which we said last time can arbitrarily be set at 0.5 or 50%, which makes sense intuitively, but it doesn't have to be. So that's another example, and I think these are the two hyperparameters we've learned about so far, but there's many others that we'll learn about throughout this class. So,
What was the first one, the regularization strength?
yeah, and we'll cover regularization in more detail later. Yeah.
So this validation data, is it like a subset of training data, or is it its own thing?
It's its own thing, but you use it during the training process. So the reason you don't use the validation data or the test data to do validation is that the validation data is used to make decisions during the training process. So it'd be kind of cheating to then test the model on that, because you're optimizing the hyperparameters and then testing on that same data set. So it's kind of cheating. So you want to split everything up so that you know how your model generalizes to new data. But typically you don't want to do it with training data because the model parameters are fit with those, and the hyperparameters are this independent things. You want to make sure your hyperparameters also generalize. Yeah.
In the real world, are all of the data basically exactly the same kind of thing? You're just sort of arbitrarily dividing it up into subsets of certain size? Or is there something qualitatively different between the types of data in the sense?
No, they should all be of the same format.
Same size.
Exact same format. Just like in this example, they're all the same format. It's always the case because a model is trained on a specific format of data, so it can only make predictions on that same format of data. But you can get creative with how you define that format and then get things like ChatGPT, but that's beyond the scope of this class. But take the deep learning class, because I think that probably covers it. Or take my human-centered AI class or human-centered data science in the fall, and we'll cover that type of stuff as well. Okay, so now with all that background, we will go into finally what's needed to answer question number 2 on the homework. So if you've looked at the homework, you will have seen that there's this thing called a ROC curve, which stands for a receiver operating characteristic, ROC curve. And this is a very, very, very commonly used way to evaluate classification models and binary situations. So as we talked about before, we kind of had this decision last class that we'll just go with a logistic regression cutoff of 0.5. So we said the default logistic regression cutoff was 0.5, and we said that if the prediction outputted by the model, so if y hat, let me write this differently. So if the output to the model y hat was greater than or equal to 0.5, then predict 1, and else predict 0. But it doesn't have to be 0.5. So let's define an ROC curve and talk about the thresholding of a model. So a ROC curve plots two things. The x-axis is the false positive rate, often abbreviated as FPR, and the y-axis is the true positive rate, often abbreviated as TPR. So what are these metrics? Well, true positive rate has some other names. It's also called sensitivity, which we learned about, which is also called recall, which we learned about. And as we learned, it has this formula, true positive over true positive plus false negative. And the false positive rate is basically what happens when you flip each of those elements. So it's the false positives over the false positives plus the true negatives. As you choose different decision thresholds, so 0.5, let's say you made it 0.7 instead, the false positive rate and the true positive rate will differ. So what we do in a ROC curve is we the decision threshold and plot corresponding false positive rate, true positive rate as a point. So we might plot that here for one threshold. We might change the threshold and get, actually I'm going to draw this slightly out here for pedagogical reasons. So let's say we change the threshold and we get that combination of false positive rate and true positive rate. We change it again and we get that combination. The maximum false positive rate would be 1. The minimum is 0. The minimum true positive rate is also 0. The maximum is 1. I'm going to draw some dotted lines here. Okay, so we might do this for several thresholds, and at the end we connect the dots. Let me go through this and then I'll take questions. So that's what we do. I want to think through what happens under different scenarios. So let's first think through what happens if we have a perfect classifier. So if we have a perfect model, so let's draw this. So this is false positive rate, true positive rate, da 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 da. Okay, so if we have a perfect model, what's gonna happen, oops. Oh, here we go. Okay, so if we have a perfect model, our false positive rate's always gonna be 0. And we'll get a perfect true positive rate in all cases, except for one case, and that's going to be when the decision threshold is 1, because when the decision threshold is 1, we predict all zeros. We don't predict any positives. Sorry. When the decision threshold is 0, we predict all positives, so opposite of what I said. If it's 0, it's all 1s. So the true positive rate is going to be 1, and the false positive rate will be 1, because everything's a positive prediction. So in that scenario, a perfect model would have the following AUROC curve, and we'll see why I'm shading this in a bit. So that's one scenario. This is the ideal AUROC curve. Never happens in practice. Let's say, on the other hand, we have a random.
So this model right here, is it like when everything's positive, is it?
That's just this last data point. Oh, wrong color. That's this data point over here. So, let's draw it over here. So, I'm going to make some extra room. Yeah, let's think through the different cutoffs and what they mean. So that's a great point. So if the cutoff is equal to 0, that means we only predict 1, and that would correspond to that point here. And you could think through why, but the reason is because everything's positive, so therefore the true positive rate's 1, the false positive rate's 1. The other extreme, let's say the cutoff is equal to 1, that means we only predict 0. That would correspond to this point here, because let's make clear this is an arrow. Because that's still not an arrow. Is it clear that that's an arrow? Okay, sorry, I'm getting hung up on that. So in that case, everything is predicted to be a 0, so the true positive rate's 0 and the false positive rate's 0 because there's no positive predictions. The numerator is 0, no positive predictions. So if we start going down, let's say we have a threshold close to 1, so let's say the cutoff, when the cutoff is equal to 0.8, well, in that case, we're predicting mostly zeros, but some things are positive, but very few because we have such a high threshold. So as a result, the the false positive rate is going to be relatively low because you're not really predicting positive to. Sorry. So when the cutoff is 0.8, we're predicting mostly zeros. And because of that, the false positive rate will be a little bit lower. And ideally, the true positive rate will maintain its highness, but in practice, that doesn't happen. So that might correspond to here. And using the same logic, but for a low threshold near 0, that might correspond to this point. So using that, let's go back to what happens with a random model. So in a random model, we have false positive rate, true positive rate. So when we can't really change what happens when the threshold is 0 or 1 because that's, in that case, it's going to be predicting all 1s or all 0s, so we're going to get those same extreme values. But let's say the threshold is 0.5 and the classifier is predicting randomly, then you'd expect roughly 50% of the points to be correctly predicted and 50% to be incorrectly predicted. So we might get 50-50 for true positive rate, false positive rate. Let's say you increase the threshold, say to 0.8, then you might expect that even though most of the data points are being predicted as 0, the number of things that are randomly predicted as positive are going to be roughly equal in terms of whether they're correctly predicted as positive or not. They'll just have a slightly lower rate than 1, so that would correspond to this point. Similar logic for 0.2. And so what you end up finding is that for a random model, the ROC is the diagonal. And for a model that is in the middle, so it's not random, but it's not perfect, and this is the usual case. So the usual case being that let's just write it in English. So better than random. Than random, but not perfect. We end up getting something in the middle. So we have our false positive rate, true positive rate. Drawing these dotted lines to just guide where the 1s are. And now I'll draw the diagonal to signify what a random guessing model would be. We can't avoid this situation when the cutoff is 0 or 1. And we'll get a curve that kind of looks like this, where the higher the curve is to the upper left corner, the better the model does. And the way we tend to quantify how good a ROC curve is using a metric called the area under the ROC. And sometimes we just call that AUROC, and that's exactly what it sounds like. It's the area under the ROC curve. So for a random model, random guesses, that is, the AUROC will be approximately 0.5. For a perfect model, The AUROC is, well, it's going to be exactly 1. In practice, nothing's exact, but we'll just go with exact. So AUROC equals 1, and in practice, the AUROC is between 0.5 and 1, with higher AUROC, meaning better performance. The reason we like using AUROC is that all the other metrics we learned about, accuracy, precision, recall, F1 score, sensitivity, specificity, they all are for a specific threshold of your model, say specifically when the cutoff is 0.5. But with what a ROC curve allows you to do is look at how does the model generalize to a variety of different thresholds. So that's the AUROC curve, very commonly used. It's easy to visualize, so a lot of times in machine learning papers you'll see these plotted, and nice thing to do for your project. But it's also quantifiable. It's a number between 0.5 and 1, and that's easily comparable when you take the area under that curve. So that's why machine learning people love AUROC. Yeah.
Could you go back to the origin?
Yeah.
So 0.8 is that. 0.2 is that.
Oh,
But
yeah.
how come it's 1 at the very bottom then? Don't you mean the other way around for the last 2 numbers?
So when the cutoff is 1, that means that it's only predicting 0, and that means you're not predicting any positives. And if
Then
you're,
how come it looks as though the answers are flipped though? Because it's like the cutoff is 0 is at the top, but at 0.8 is closer to 0.
no, yeah, so exactly. So when the cutoff is, yeah, maybe these are not drawn clearly, so let me redraw this in a easier to see way. So 0 is here, 0.2 is,
Maybe you use different colors to do the arrow.
oh yeah, good idea. So 0.2,
Ah,
oh, I guess this might be a slightly
okay, that
poor,
makes more sense.
yeah. Yeah, sorry, they were all jumbled up. I apologize. I'll just draw the cutoff equals 0 when we only, the cutoff equals 1 goes there. Okay.
I have a question. What's the decision threshold?
So decision threshold is we covered this last time in logistic regression, but it's basically the cutoff. Wait, I think we wrote it here too. So if the decision threshold, for example, is 0.5, that means we predict 1 if the classifier outputs anything above 0.5, and if it's below it, we predict 0. If you can make that threshold 0.8, and people often do change the threshold to make the model have better performance, and in that case, you only predict 1 if the model outputs a probability greater than 0.8.
So in the green part, the decision threshold is 0.5.
In this up there, on the
Yeah.
top? Yeah, that's
I
0.
think decision threshold and cutoff mean the same thing.
Yeah,
Oh,
yeah.
okay.
Wait, sorry. I have a question.
Sure.
I'm misunderstanding this. If the threshold and cutoff is the same, when it, I guess I don't understand how we predict 1 when the cutoff is 0.
So when the cutoff is 0, that means that if y hat is above 0, we predict 1. And if it's below 0, we predict 0. So therefore, we're always predicting 1.
At that point.
Yeah.
Oh, okay.
So you're creating this this ROC curve, which you can take the AUROC of, for a bunch of different threshold values. So you're seeing how does the model behavior change with different threshold values. Okay, any other questions? This is a homework question, but you know about logistic regression, you know what the output of logistic regression is from the equation. You know how to calculate false positive and true positive rate for different thresholds, and you know how to plot stuff, and you know how to find the area under a curve. For the homework, you're not gonna have to do integrals. You can use geometry with like rectangles and triangles to calculate that area in the homework. So no integrals needed for the
But I
homework.
don't understand about, question 2.
Mhm.
You've given an x1 and x2 and a y. And I don't know how you would plot that. Can you
Mhm.
so, like one of them, like you've got 3 coordinates. I know after the 2-dimensional plot.
Mhm.
So I'm not sure how this would actually look.
It would be the same. The ROC curve would look the same as we drew it, even if there were x1 through x 10,000, because the output to the model is still 0 or 1, and all you're using to create the ROC curve is the zeros versus 1, is comparing what's predicted with what the true value is. That's the only thing you use to create an ROC curve.
I'm confused though. You only have. I'm missing something.
So you have a model here that it happens to take 2 inputs, but this problem would have worked the same if it were 10,000 inputs. But regardless of how many inputs it takes, it outputs a number between 0 and 1. That's its prediction. So given x1 and x2, you can figure out what the prediction is using the logistic regression equation and the learned model weights. And you can compare that with what the true value should be, which is labeled here as output y. Maybe it would be less confusing if I label that as true value.
So
But
this is the true. So y is the true value, and x. These are 2 inputs, and we're supposed to use another. Oh, okay. We put them into that equation and then get the predicted value.
yeah, exactly. And once you have the predicted value and the true value, you can calculate.
Okay. So I'm just confused. I thought those x's and y's were supposed to.
No, yeah, no, this is part of this question. It's a little confusing specifically because it requires understanding the full process of machine learning to answer it. So it's designed that way on purpose. Any other questions?
So the ROC curve lets you pick a decision threshold that, like, based off if you want to capture like all your true positives versus like if you want to limit like false positives. Then.
Yeah, exactly. And in different use cases, I think we use the diagnosis example. You might have a different threshold that you want, depending on your use case. Any other questions about ROC? Okay, so one more concept that actually turns out to be used in question 4 of your homework. So I guess after today, you'll know all the concepts you need for the homework, and then if you know Python, you could start your homework now, otherwise next week. That concept is called cross-validation. And this is commonly done, a commonly used evaluation tool, where the issue is that, let's say you're splitting your data into a train set, validation set, test set. How you split up your data is kind of arbitrary. Is it just how your data points happen to be randomly ordered could affect things? What percentage you put in the train versus test can affect things. There's a lot of randomness to the process. So if your data points happen to be sorted differently or ordered differently, you'd get a different model that's trained, as well as different predictions on that model. So to protect against that somewhat, it's not a perfect process, but to help protect against that, it's common practice to do something called cross-validation. So we, again, are drawing this rectangle to represent the data set. And what we do in cross-validation is we split up the data into into train and test sets. You also, and validation set, but I'm not gonna draw that here, but same concept. In many different ways. So for example, you might first split up the data how we first talked about. So this, let's say 70% of the data is the training data and 30% test data. Actually, let's make it 80-20. That'll be cleaner for things you'll see in 1 second. Okay, so that's one way we can do it. But we could also have this part of the data be the test set and the rest of the data be the train set. So this portion of the data goes in the training set and the part to the right of the test set also goes in the training set. So that's another way we could split it. So what we do in cross-validation is you specify a number of folds. So here I'm going to draw 5-fold cross-validation. Okay. So we can have test here, train here, and train here. So in these, everything below the first fold, the training set collectively consists of the left side and the right side. In fold 4, test set is here, train, train, and finally test. Oops, shouldn't be a line there. Oh, I drew the line again. Oh, okay. Train. This would be called fold 1, fold 2, fold 3, fold 4, and fold 5. In general, cross-validation is usually called K-fold cross-validation, where K represents the number of folds that you split the data into. Number of folds. And the way you evaluate the model, so to evaluate the model, you average the performance over the K folds. Pretty simple. Average the performance over the K folds. And if you're doing it really scientifically, you put the standard deviation as well, not just the mean. So in your homework, I think you're supposed to implement 10-fold cross-validation given a data set. And you'd want to split it up in this way. And then I think you get extra credit if you make K an input and you make it work for any number of folds. Just because that's kind of a fun programming exercise. Might be like a coding leak code question. But so if you, I don't know, extra credit, it's not required. The coding for this class won't be leak code level. Okay, any questions? Yes?
So is the test set for each fold, is it, in this case, you did 20%, 80%? Does that come from the 5 folds, or can you pick any?
Yeah, I think usually it does. Yeah, so through your homework, you'll do 90-10.
10%
Yep.
test in each fold then?
Yeah, exactly. Yeah.
So false positive is where y hat is 1 and y is 0?
Yeah, so false positive is when you predicted it to be positive and it's not positive.
when you predicted it to be
0.
0, but it's actually
Yeah,
positive.
so y hat 0, y 1.
Y is 1. Okay, so. Alright. Thank you.
Yeah. Yeah.
Is this sort of standard practice where you always be expected to do this kind of thing? Or instead of just, like, if you wanted to be sort of a little sloppier, you could just randomize your entire data set and then just pick your test set at random, and maybe that would be good enough. But
Yeah.
this is sort of a standard practice.
This is very standard practice. It's not universal practice, but you could be, if you're a peer reviewer, you can ding someone for not doing this, for sure. I mean, sometimes there's good reasons to not do it. Maybe it takes a week to train the model, and doing cross-validation's infeasible. Maybe that you want to evaluate the model on completely different data that hasn't been collected during the training process. The real world, there's some reasons to not do cross-validation, but unless there's a good reason to not, you should do it. But there are good reasons to not do it. Got to know the rules before you break them. As someone who likes breaking rules. Oh wait, this is recorded. Okay, any other questions? Okay, so that's what you need for homework 1. I don't want to switch to programming. That's the next thing that I would have talked about. So instead, I want to start covering things with a little bit more mathematical rigor than we have been doing. We've been basically using algebra. So I want to start including calculus, linear algebra, and probability. And as we learn each of those concepts, see directly how they're used in machine learning. So let's start with calculus and just a review of calculus, because everyone here's taken calculus, right? It's a prereq for this class. Okay. I gave everyone override, so I guess in principle you might not have taken it. But has anyone not taken it?
Does it count if the last calculus you did was 35 years ago?
No, that's the best situation to
I
be.
don't think so.
Okay, good. Great. So we'll do a quick calculus overview anyways, just the parts that are relevant to machine learning, or I should say the types of machine learning that we are doing here, which is the types that you typically first learn about. So calculus review. Let's say we have an equation, y equals x squared plus 1. I'm going to go quickly through this because most of us have already taken calculus. We could plot that as the following. So x, y. That would result in a parabola. Oh my gosh, my art is, imagine it shifted a little bit to the right. In calculus, we have this concept of a derivative. So the derivative, as we all know, is also written as y hat, also written as the derivative of y with respect to x, and you could also write it as the derivative of x squared plus 1, which is y, with respect to x. And what it represents conceptually is no need for quotes, maybe an arrow, instantaneous rate of change of y with respect to x. So if we have the way we can measure instantaneous rate of change is by taking the slope of the tangent line of the function. So for example, let's look at three just 3 points on the parabola, one here, and one up there. So here, the slope is going to be equal to 0 because yeah, I mean, the slope of that tangent line is 0. Over here, the slope, assuming I drew this with high fidelity, which is not the case, but would be 2. So it's a positive slope. And over here, the slope is negative, and it's notably of a higher magnitude than the corresponding point on the right of the parabola. The slopes of the tangent line can be really useful for the learning process of this gradient descent concept. We'll come back to that. That's not for today. But think of y as our loss function and x as our parameters, and we're optimizing. That's why we care about derivatives, but we'll come back to that after we learn about programming. So probably not next week, but the following week. There are derivative rules, and in this class, I don't expect you to memorize the derivative rules. You learn a bunch of derivative rules in calculus class, and it's not really, I don't know, the concepts are not super pedagogical to go over those. So if you ever need a derivative in this class, I'll give it to you. But for example, there are derivative rules that tell us that the derivative of the function we drew is 2x, and which means that the slope of the tangent line of our parabola given x will be 2x. So if we spot check this at x equals 0, the derivative gives us 0, so that checks out. At x equals 1, oh, this is x equals 1, by the way, the slope of that tangent line is 2 times 1, so 2, etc. So this derivative gives us an equation for the slope of the tangent line of the formula that we're taking the derivative of. And for rules for calculating derivative, see calculus class for derivative rules. Again, it's not intellectually stimulating to go over those rules, so we'll skip that, but just know that they can be calculated. In many cases, there's actually a lot of functions that can't be differentiated, which can be problematic in machine learning, and we'll talk about why.
You mean the infinite derivative?
There's various reasons why they're not differentiable. So there's also a concept of a partial derivative. Have we learned about partial derivatives? Okay, cool. So this will be review. But so partial derivative is the same concept, but when you have a multivariable function. So for example, if you have f of x1, x2, x3, common situation in machine learning. So let's say that would be 3x1 to the 5th minus 12 x1 x2 plus 2 x3, I'm just making up this equation, minus 5. There are derivative rules that would tell us that the partial derivative, and it looks kind of like a d but slanted, partial derivative of that function with respect to x1 would be 15 x1 to the 4th minus 12 x2. Basically, you treat all the other variables as constants. So x1 is not a constant. Everything else is constant. Derivative of a constant is 0. So that's how we get that. We could do the same thing for the partial derivative of our function with respect to x2, which in this case would be negative 12 x1. Exactly how we calculate this doesn't matter. Again, see calculus class. Partial derivative of f with respect to x3 is just 2. And the name of gradient descent, which we haven't covered yet, but a lot of you have probably heard of gradient descent, and if you haven't, we'll have a whole class on it. So a gradient is a vector of the partial derivative of each of our variables sequentially. So partial derivative of f with respect to x1, f with respect to x2, and f with respect to x3. That would be called a gradient. And maybe just a note, as in gradient descent, which is a very popular algorithm for learning the parameters of a model. Yes.
And they're essentially the Jacobian.
Yeah, we'll okay. So I want to quickly get to how we optimize functions, because now that's going to build up towards gradient descent. And we can use calculus and derivatives to optimize functions. And you learn this in calculus class, so should also be a review. So optimizing functions. You'll notice that if you have a function, its maximum and minimum points are where the derivative is 0. So this is a maximum point, derivative is 0. This is a minimum point, derivative is 0. This is another local maximum point. Local is an important precursor to minimum and maximum. So these are local minimum and maximum. And we notice that that occurs where the derivative is set to 0. So to optimize a function, the procedure is to set the derivative of the function to 0, and then let's do it in the one variable case. So this is x, this is y, and then solve for x. And that will tell you which x gives you a local minimum or maximum. Using this method, you don't know whether it's a minimum or maximum, but you can compare them and see. We will deal with functions that only have local minimum, so we don't have to deal with that problem. But we'll get there. That's not for today. But let's just look at an example. So let's say that we have following function. So f of x equals x minus 3 to the 4th power plus 4. The derivative of that, so the derivative of f with respect to x is going to be 2 is going to be 2. Oh wait, sorry. I meant to put a squared here just to make it easier to draw. So that's going to be 2 times x minus 3. And so the derivative function, if we plot it, would look like this. Sorry. Actually, let's not plot that. Let's plot the actual function. That'll be more clear. So let's plot f of x with respect to x. So f of x, it's a parabola. It should be a parabola. That looks like something else. And we'll notice that the minimum of this function occurs here. So we have a function for our derivative. We can set our derivative now to be equal to 0. And now we solve for x. So 0 equals equals x minus 3, x equals 3. And it turns out that that corresponds to this point here. So, and you could plug in 3 back into the equation and you'll see that we get 4 as the output because that whole first term is 0 plus 4 is 4. So that is how we find local, minimum, and maximum functions. Any questions so far? That was like half of calculus in a few minutes, so I hope that's okay. Good, yes?
I'm vaguely trying to remember the process you went to get from the first line to the second line.
Mm-hmm.
Was taking the exponent and multiplying it by the coefficient.
Yeah, so it's a derivative rule, but it's that, yeah, you take the x, the rule is basically,
I guess I don't, as you said, you're gonna give us the stuff.
yeah, but just, because I use in this example, the derivative of x to the n power equal to n times x to the n minus 1 power. So you don't need it for this class, but just to make this example workable, I think it's useful to have that. Okay, and then I guess the last note is that you could imagine as a sneak peek to gradient descent, or how we actually do that last piece of the machine learning process, how do we actually learn the parameters, where you could imagine in machine learning, what we have is our parameter space, and we have our loss function, which can be a variety of different things. And a good loss function will have the property of being convex. So a convex function is one that looks like that. And therefore, if we have a function that looks like that, which is convex, we're guaranteed to find a local minimum. That's precursor to gradient descent. We're working towards it. Unfortunately, next week we're covering Python, so we'll come back to all this in 1.5 weeks.
What if you have a concave loss function? What happens? What would that would mean?
Concave. Then you wouldn't ever minimize your loss function, and that wouldn't be good, because you wouldn't find the optimal parameters, because you want to minimize loss.
Wouldn't the trick be then what's local?